We're going to take a look at how we can utilize vector value functions to derive our formula for projectile motion in 2 dimensions. So let's say for some reason that we are looking at the projectile of mass m, and the force due to gravity according to Newton's second law of motion is F equals ma, or F equals negative mg with respect to j. All right, so this is, and remember it's negative because gravity has that downward positioning. All right, so our mass is going down in the down position with respect to the y-axis, which is j. Right? And then F is ma, mass times acceleration. So if we just set these equal to one another, ma equals negative mgj, we can find that acceleration is equal to negative gj. Right? And then what we're going to do is what we looked at in the previous 2 sections. That's an acceleration function. So what we can do is we can take the antiderivative twice to be able to get to the position function. And so right here we have the velocity function, right? And we just integrate the acceleration. Integral of negative gj is going to be negative gtj plus c1. Right? And in this case, if we set t equal to 0, c1 is just going to be equal to the initial velocity. Right? So that makes it pretty easy. We're going to do the same thing over here, and we're going to integrate the velocity function. So if we integrate negative gj or gtj, that becomes 1/2 gt squared j, and then we have the c1t and c2. Now remember, when we substitute 0 in, these two are going to cancel out. We're going to be left with c2, and we're going to call c2 r naught, the initial position, okay, or the initial height of this thing. Okay, so just keep in mind that that's where these variables are coming from as we go along. All right, so we substitute back in, and using C1 as V naught, C2 as R naught, then we get this equation. All right. Now, let's also consider the unit circle definition of x and y. So the velocity, or the initial velocity, we can define as xi plus yj, and we just use the unit circle definition. So we have the magnitude times cos, magnitude times sine. This is just a circle of radius v naught, and it just becomes this statement right here. All right, so we're going to substitute that back in for v naught. We're also going to realize that r naught is going to be the initial height, so that would be h times j. And so we just substitute everything back in. So we're just plugging this back in for v0, and then for r naught, we're substituting hj. And eventually, what we end up with is this position function. Right? And so that's the function that we're going to use to be able to solve problems with respect to these vector value sorts of things, with respect to projectile motion. Right? So and remember that gravity, 32 feet per second or 9.81 meters per second squared, depending upon which unit you're working with. So given that, we're going to look at a few examples. So I'm just going to copy and paste this function because we're going to need this a couple times. So we'll cut and paste that right there. And a couple examples. So we have a projectile fired at an initial height of 3 feet above the ground with an initial velocity of 900 feet per second and a 45-degree angle. Create a vector value function to graph the path of the projectile. Determine the maximum height of the projectile. Determine the distance traveled by the projectile. All right, so if we do this, all we know, or all we need to know, is that in the problem we're given the initial height, so h is equal to 3. We're given the initial velocity, v naught, which is 900 feet per second, and then we're also given the angle theta, which is going to be 45 degrees or pi fourths. creating a vector value function. We're just going to substitute all those values back in and simplify. All right, so r of t is going to be equal to 900v, or 900t, times the cosine of theta, so that's cos of pi fourths I, plus the initial height, which we said was 3 feet, the initial velocity, which was 900, times sine of pi fourths times t, and then minus 1/2 gravity squared, now gravity times t squared, excuse me, and because we're dealing with feet per second, we're going to end up using the 32 feet per second squared for g, and that's in the j direction. And if we simplify that, remember cos and sine of pi fourths are equal to root 2 over 2. And so we end up with r of t, simplifying, is going to be equal to 450 root 2 ti, okay, plus 3 plus 450 root 2 t minus 16t squared, and that's in the j direction. Squeeze that j in there. All right, so this is our function. All right. And it might be worthwhile to note that this tells us, this 450 root 2t, that tells us the x position after time t. So let's define x of t to be 450 root 2t, and let's define y of t to be equal to 3 plus 450 roots of 2t minus 16t squared. Right? And again, that's just because that's the coefficient of the j. All right, so now we're asked to determine the maximum height of the projectile. All right, and that's pretty easy. The maximum height is just found by the derivative. So we're going to find the derivative, okay, and then that's going to tell us what the optimal time is, and then we're going to substitute that time back into the original y function. All right, so height, remember, is defined by t, so we're going to find, now this is letter B, we're going to find y prime of t, and that's going to be 450 roots of 2 minus 32t, and its optimal value is the critical value, where that derivative is going to be equal to 0. If we were to solve for t, this implies that 450 root 2 over 32 is equal to t, and 450 over 32, I think that's going to be 225 over 16, which it is. All right, so that ends up being 225 root 2 over 16. Okay, now that just tells us what the time is. It does not tell us what the height is, or the maximum height. Okay, so the maximum height of the projectile is going to be when we substitute this back in for y at t. Okay, now I'm going to approximate this just out of convenience. So if I approximate that, so 225 root 2 over 16, that's 19.9 approximately, and that's in seconds, since we had feet per second. All right, so let's hold on to this, and we're going to substitute that back into y and get an approximation. So y at 19.9, not y prime, but y, okay, is going to be equal to 3 plus 450 roots of 2 times 19.9 minus 16 times 19.9 squared. Right, and again, I'm going to get an approximation for this, and that's going to find what the maximum height of the projectile is. So 450 roots of 2 times 19.9 minus 16 times 19.9 squared. And I get 6331.1. And that would be in feet. So hopefully that makes sense as to how to figure out what the maximum height of the projectile is. And our last problem, determine the distance. Okay. If we were to determine the distance of this thing, now remember when it's fired, it sort of looks like this, and this is going to be a really bad drawing, but when it's fired from the initial height of 3, that's what the path should look like approximately. All right, and right here, that's our point when t is equal to the 19.9. Okay, so it's just a quadratic. Right. And so what we're going to do is we're going to try to figure out this time right here. Okay, so this time is equal to, don't know. Right. So if we know that time, then we can just substitute it back in to x of t. So we could just say t at that point is going to be our x of t. So x at that point is going to be equal to the total distance. All right, in the x direction. So to be able to solve that, we need to figure out when the height is equal to 0. And so what we're going to do is we're just going to go up here and we're going to set this function equal to 0 and solve. Okay, so I'm going to set y of t equal to 0, which is going to be equal to 3 plus 450 roots of 2t minus 16t squared. Right. And it might be helpful for us just to have that 450 roots of 2 as a decimal. So that's 636.4. And we're going to use our quadratic formula to be able to approximate this. Okay. So we're going to get the opposite of 636.4 minus the square root of 636.4 square minus 4 times a, which is negative 16, times c, which is 3. And we're going to divide that by 2a, 2 times negative 16. All right, and this should be plus minus. Right, so give me a moment, I'll shove this into the calculator. So that's going to be 636.4 plus square root of 36.4 square minus 4 times negative 16 times 3. And we're going to divide all of that by negative 32. All right. So I get that one answer, which is not looking promising, is negative 39.7 or 39.8. And hopefully we get a different answer when we plug in the negative, and we get 0.004 for that one. Oh, I know what I did there. I apologize. The first term should be negative, and I did not make it negative. All right, so I get t is equal to negative 0.005, and I'm assuming if I change this to a negative, that's going to give me positive 39.8. Okay, there we go. All right, now clearly this one doesn't make any sense because we can't have negative time. That's over here. So this little snippet right here, that's when t is equal to negative 0.005. Right here, this is where t is that 39.8. All right, and mercifully to finish this off, all we're going to do is we're going to find x at 39.8, and that's going to tell us the length traveled. So 39.8 is going to be equal to, or x at 39.8 is going to be equal to that 450 roots of 2 times 39.8. And I'm just going to plug that in. and I end up with 255 or 25328 0.6. Okay, and that would be in feet. Okay, so roughly a little bit less than half of a mile if I was going through and trying to approximate. All right. So hopefully this illustrates the derivation of the projectile motion formula, and then also an application of this. And we're going to look at one other application in a moment at our last video for this section.